Hello everyone, and welcome back to the final tutorial video for our course. In this video, by a student request, I wanted to cover how to perform function convolutions. But I also decided, as I was going through and writing up these solutions to your mock exam 3, that while I was at it, I might also show a quick example of how to use convolution theorem to help calculate Laplace transforms. I'm going to cover both of these with one example in this video. So, what does convolution theorem state? Well, convolution theorem states that if you take the Laplace transform of a convolution of two functions, as you can see here, that is equal to the Laplace transform of the first function times the Laplace transform of the second one. And of course, to calculate convolutions, say you take the convolution of a function f and a function g, that's going to be this integral here, which is the integral from 0 to t of f of tau times g of t minus tau d tau. Generally speaking, we use tau to indicate the convolution variable. It's really just a dummy variable. It doesn't matter what you call it. Almost all the literature, the textbooks, etc. use the variable tau, so that's what I'm going to go with. But you could call this Y, you could call this John, you could call this Annette. It really doesn't matter what name you give to this dummy variable. It's going to go away when the convolution is done, no matter what happens. Okay, so in this video, what I'm going to do is I'm going to take a slightly simplified version of the final problem on the mock exam. This is going to be somewhat similar, at least, to the problems that the final problem on the final exam. And I'm going to show very quickly how we would use convolution theorem to be able to relatively simply solve the problem, and then I'm going to go through the process of calculating the convolution. Alright, so here is the slightly simplified problem that I want to go over. Let's say that I have given you an initial value problem, and you have taken the Laplace transform of both sides, you've worked through it, and you've solved for the Laplace transform of x. So you've gotten to this point. You have found that the Laplace transform of the function x that you're looking for is equal to the Laplace transform of t squared times the Laplace transform of e to the negative t. Now, the only thing that you have left to do at this point is to find the actual value of x of t. Now, one thing that you could genuinely do is you could actually take both of these Laplace transforms. You could calculate these. Both of these should be easy to do with table 7.1.2. You could multiply them out, and you could calculate these and say use partial fraction decomposition. I want to be very clear with this. If you are going through my solutions, my solution write-up to mock exam number 3, I did in fact use in the final problem convolution theorem to solve it. But I want to be very clear that it was totally possible to not have to use convolution theorem to solve it at all. Convolutions and convolution theorem are just one tool in your toolkit. In many cases, there are several ways, several roads that will lead to Rome, as it were. And you don't always only have one tool that will do the job. However, I did use convolution theorem in this case, and I'm going to use this as an example of how to use convolution theorem and also how to calculate a convolution when you're actually at it. So, we could use partial fraction decomposition, but let's not here. In this case, I want to tackle this with convolutions. Okay, well, how do we do this? The first step is to use convolution theorem. So by convolution theorem, and keep in mind that this is theorem, I believe, theorem 1 from section 7.4. We are given, in fact, we know that our function x of t has to be equal to the convolution of t squared with e to the negative t. Okay. We got this directly from convolution theorem that I've written up here right up above, as you can see. basically all I did is I took this guy up here. I'm now circling in red. And I took the inverse transform of both sides. And you can see that if you take the inverse transform of both sides, all the transforms and the inverse transform are going to cancel each other out on the left-hand side. And you're going to end up with something that looks very much like this. Okay. Now, hopefully you can see how convolution theorem was used. Convolution theorem itself is very straightforward. It's a very useful theorem. It's very helpful. It tells you how to work with the inverse transforms of a product of transforms. Very easy to apply, and I believe on your homework set 9, you had a number of problems that asked you guys to use convolution theorem and to just write the solution in terms of a convolution integral. So you basically had to get to this step, and then you just write this as a convolution, and it didn't ask you to calculate it. However, in the final problem of the mock exam number 3, as well as in the final problem of your final exam, I asked you guys to calculate the entire thing. In cases like those, just leaving it as an integral is not really pleasant. You want to know what the exact value is. So, when you're applying convolution theorem in cases like these, the issue with it is that it leaves you still with a convolution you need to calculate. We need to calculate t squared convolved with e to the negative t. So, that's what I'm going to spend the rest of this video doing, and hopefully this will serve as an example more generally of how to calculate the convolution of two functions. Okay, so what we want to do now is we want to calculate this convolution. We have one function is t squared, and the other function is e to the negative t. We want to convolve them, so let's just use the formula. So we know via the formula that t squared convolved with e to the negative t is equal to the integral from 0 to t of tau squared times e to the negative t minus tau d tau. Now, again, to reiterate, if you don't want to use tau here, you can use any other variable name that you want. You can use x, you can use y, you can use z, you can use really any name. I'm just going to use tau to be consistent with all the literature as well as with your textbook and with my lecture notes. Okay, so let's simplify this a little bit. We have a negative in that exponent. We can multiply it out, and we'll get that this is the integral from 0 to t of tau squared times e to the tau minus t d tau. Okay. In other words, this is going to be equal to the integral from 0 to t of tau squared times e to the tau times e to the negative t d tau. And here is something that is actually very important to keep in mind when calculating convolutions. The variable t, this guy right here, this is treated as a constant. And if t is a constant, that means that e to the negative t is itself also a constant. And what can we do with constant multipliers inside of integrals? Well, we can pull them out. In other words, we can pull e to the negative t out of this integral from 0 to t, which leaves us with tau squared times e to the tau d tau. Okay, this is sort of what you should, or what I generally advise that you try to do if you're not comfortable with these integrals, if they're sort of looking a little bit strange. Try to pull all of those t terms out of the integral because they are treated as constants, so there's usually ways that you can do that. Sometimes you might need to use some sort of trig identities, sometimes you need to use laws of exponents, and sometimes you just have t multiplying and you just pull it out directly from the integral. Regardless, try to move it out so that you're left with only taus inside of the integration itself. Okay, we still have an integral left to calculate over here. And the question is, how do we calculate this? Well, In this case, as will happen at least relatively frequently in cases like these with convolutions, we're going to have to use integration by parts. So let's integrate this by parts, and let's write this perhaps in blue. And the u I'm going to use is going to be tau squared. The v prime I'm going to use is e to the tau. That means that v is also e to the tau. And of course, u prime is going to be equal to 2 tau. All right. So by integration by parts, what have I gotten? Well, I still have that e to the negative t out in front. And what is it multiplying? It's multiplying over here. We're going to have u times v, in other words, tau squared times e to the tau from 0 to t, minus the integral from 0 to t of, here we're going to have 2 tau e to the tau d tau. Now, just to be clear as to exactly what I did here, I like to color code my substitutions, at least so that you guys can see what I'm doing. This u is equal to tau squared is what's substituted into here. That is being multiplied by this v is equal to e to the tau, which is here. It is also here. And then, of course, this u prime belongs right here. Okay, now let's multiply this out, plug these values in. And what do we see about this guy over here? Well, we see that when tau is equal to 0, because we have a tau squared in front, this is going to be equal to 0 when tau is equal to 0. And this guy is going to be equal to t squared times e to the t when tau is equal to t. So what we're going to get, when tau is equal to t, those e's, those exponents are going to cancel each other out, and we're going to be left with a t squared. And when tau is equal to 0, we get a big fat 0 there, so we don't need to worry about that. So we're left with t squared minus 2 times the integral from 0 to tau of tau e to the tau d tau. And I'm going to use integration by parts once more. This time u is going to be tau, u prime is going to be 1, v prime again is going to be e to the tau, and that means that v is going to be e to the tau as well. Okay, so once more by integration by parts. Oh, and I forgot up here, I made a mistake, I apologize. Let's use a smaller eraser for this. I forgot a term here. This should be 2e to the negative t. I dropped that. My apologies. All right, so we're left with t squared minus 2e to the negative t times. This time we're going to have tau times e to the tau from 0 to t minus the integral of e to the tau from 0 to t. And once more to color code where everything is coming from. This guy is this guy. This guy is both this and this. And this one is exactly what's being sort of implied right there. Okay. So, once again, very similarly to before, let's look at the value of this guy. This guy is going to be equal to 0 when tau equals 0, and this guy is going to be equal to t e to the t when tau equals t. So plugging all those values in, multiplying it out, this is going to give us, we're going to have our t squared minus 2 times t, because again, the exponentials are going to cancel each other out. Now what we have left is this last term. So here we're going to have that minus becomes a plus 2e to the negative t, because we had a minus multiplying out. This guy and this guy cancel each other out. And then the integral of e to the tau is, of course, just e to the tau. And this is going from tau equals 0 to tau equals t. All right, those are our final values. Let's plug this all in. And quickly, I will note that this guy is equal to 1 when tau is equal to 0, and is equal to e to the tau, or e to the t rather, when tau equals t. And what that's going to leave us with is t squared minus 2t plus, when tau is equal to t, we're going to have two exponentials that cancel each other out, and that's just going to give us 2. Minus 2, when tau is equal to 0, this gives us 1. And so we get minus 2 times e to the negative t. And we are done. That is it with the problem. So, the moral of the story is, these convolutions are really just integrals. That doesn't mean that they're easy integrals to do, but they are just integrals, and you should be relatively familiar with how to calculate these by now. The only real pointers I have to give to you guys when it comes to calculating these is, first off, remember that inside this integral, your variable, what you thought, or what we're considering in the bigger picture to be your variable t, it counts as a constant for the purposes of the integration. That means you can pull it out if it's in any sort of factor, right? If you're multiplying by a constant inside an integral, that's the same as multiplying the integral by that constant. So, keep that in mind. First, t is treated as a constant. Second, you may need to use integration by parts whenever you are using convolutions. That happens, I would say, relatively frequently, so be prepared to do so. And third, be careful when you are plugging in your limits of integration. It is very easy to assume that it's always going to be 0 when you're plugging in 0 here. It was 0 here, it was 0 here. But keep in mind that in this case, when you're plugging in 0, e to the 0 is 1. So please be careful when you're plugging in your limits of integration, and don't drop your, don't drop a negative sign, don't drop any other things that you need to multiply out. Trust me, I did so myself several times while recording this video. All right. Hopefully this clears some things up. Again, there's really not that much to say about convolutions or about how to take them at the end of the day. Convolution theorem is pretty straightforward, and calculating a convolution is really just finding an integral. All right. Best of luck to you guys with your final in this class and with your finals in every other course that you may be taking. And I hope that you guys all enjoy your summer. Bye-bye.